Good afternoon or good evening. Welcome in this presentation entitled as Wood Log Inventory Estimation by Deep Learning. My name is Tomáš Vantuch and I will present you a few slides about that. Let's start about agenda. I will briefly introduce the company where I work for and also myself a bit. Then I will describe the problem itself. It will be followed by description of some data pipelines we use here. All of them are based on Azure resources. So basically there will be a lot of place or a lot of applications of Databricks. Then I will focus on the model itself, how it's trained, how it works, and then its results and some conclusions at the end. So Storaenso is a leading provider of renewable solutions in packaging, biomaterials, wooden construction, and paper globally. We basically focus on wood processing and pushing towards uh, more efficient and more renewable materials from these. The entitlement, the renewable materials company has its reason, and its reason is that all of we produce is based on wood. It can arise from wood constructed buildings into some simple packaging solutions for food or whatever you can imagine. As I said previously, my name is Tomáš Vantuch. I work here for almost 2 years as a data scientist. I'm responsible for image processing, especially in this case, but also I'm working with some time series and also some development around chatbots or some web services. Before that, I used to be a senior researcher at Technical University in Ostrava in Czech Republic, and my specialization was in time series analysis. So let's start about the project. As you can imagine, because we work with wood, we need to process a lot of harvested wood. Uh, Basically, it's in several places in the world. We have those mill yards, which are completely covered by wood piles, and we need to keep track of amount of those wood piles. So we basically do some inventorization of that material. It can be done by various ways, but our aim to do it as efficiently and as quickly as possible. So for that purpose, a drone-based application was developed. It means basically that some drone will fly over the mill. It will take pictures of the entire surface of all the objects there. Then those drones put together it's not those drones, but the pictures from the drones are put together into some aerial map. And this aerial map is then delivered to a human expert from the mill. His task is to identify and label all the wood inside. And because we have also a digital elevation model, it means that we have a ground amplitude of each pixel. We can then calculate the final amount of wood in the picture. But the very important key aspect is that the very precisely wood needs to be identified by a human expert. As you can imagine, this is quite time-consuming task. Human expert needs to place more than 200 different points and several coefficients there. And right after that, the wood amount can be calculated. So this was taken as an opportunity, and some machine learning model was created, not to substitute this human effort, but to save some time and to leverage this information to some quicker solution. As you can imagine, those aerial maps are quite big images. They are in TF format. On average, they have around 500 megabytes in size. because they contain those three RGB channels and also this digital elevation model. At the first stage, they are put together by Agisoft software on this map processing server on the left side. That's the place where we start. And in this raw form, they are transferred into Azure Data Lake. Now they are marked as a raw data. It's their raw stage. Here we do just some trivial sorting, and we also collect some metadata around those images. We put them together into some database, and after everything is ready, their stage is changed to production, and they are ready to be used for prediction basically. Some of those images are labeled for training purposes, and as you can see, this branch in the middle, uh, this diagram means basically that some of those images are used for model training. It's pretty simple, nothing advanced, just model is trained in Databricks environment, then it's stored in a storage account with some additional metadata about the model, basically what kind of model, what task he's solving, etc. Because those metadata are used later for model selection. We use several different models, and when the request from outside comes for prediction task, we have to decide what kind of model we are going to load for the prediction. The, the model is loaded, also the specific data for prediction are loaded, and this prediction pipeline is then executed. All the predictions are stored into the production stage in the data lake with those source images, so further investigation by human expert is then possible. We also collect some metadata about data processing and about prediction, so we can also make it or make some improvements over time. So the task itself, now you can see some images. What are we dealing with? How our mills looks like from above, and the complexity of the task relies on several pillars. Basically, we deal with different shapes of those wood piles. Not all of them are so straight. Some of them are curved a bit. Also, the color of the wood varies, and most of those variations are based on the wood type, because birch can have different color than pine and different color than spruce, etc. And also the amount of wood, the amount of water inside the wood is a significant player in these color changes, because the wet wood, as you can see, is much darker than the dry wood, which is much lighter. Also, a lot of differences in lightnings and shadows plays important role in this image processing task. And as you can imagine, low amount of labeled data, that's terrible issue in every machine learning task. We are facing that as well. Naturally, it looks like image segmentation, or more specifically the semantic segmentation task, but because we need to make it even more precise, and a lot of those wood piles are too close to each other, we need to provide also instance segmentation. What is the difference between that? Basically, semantic segmentation identifies where is the wood and where is not the wood, like what pixels are related to wood piles and what is the rest, basically the roads, object, buildings, etc. So by semantic segmentation, we can identify all objects that are representing wood piles. And by instance segmentation, we are able to separate them one from each other. And that's something what we really need, because we need to keep track of inventory of each wood pile separately. And if some of those wood piles are too close to each other, then this semantic segmentation basically outcomes for us them as one object. So as you can see, for that purpose, this model utilizes two deep learning networks. The first one predicts the objects, the second one predicts the borders, and by their combination, the final outcomes is delivered. Both of them are using the same inputs, but I will come to that later. Now about the unit model, that is pretty popular, widely used in a lot of applications, widely used in Kaggle competitions, etc. In our case, it was implemented in PyTorch framework with use of library segmentation models. I really recommend this. It's well written and easy to use. What is special about unit model? Well, it's pretty similar to any other deep learning autoencoder with one modification. Every layer of encoding path is connected to the decoding path by additional concatenation. So, like the results from those layers or those encoding levels are transferred to the decoding, and after the concatenation, the internal information is increased and the outcome is more precise. That's how it works basically. And for encoder, here we were able to use ResNet 18 architecture. It means that we just increase the number of convolutional filters. As I said previously, for input channels, we use 4 of them, the RGB and digital elevation model, and 256 times 256 is the resolution of input images. They were taken just small cutoffs from the entire aerial maps, because the entire aerial map was of resolution around 5 to 6,000 pixels times maybe 10 or 12,000 pixels. So they were pretty big and unable to be predicted at once by this unit model. So smaller cutoffs were taken and it was predicted piece by piece. And as I said, we utilized two networks, one for objects and one for borders. Image augmentation was taken as pretty necessary step here. It is again pretty common way how to increase generalization and how to increase the robustness of the model itself. The motivation or the aim is basically you are altering some features of the image that you are using for training, but you're not restoring the information which is inside, or you are not modifying the context itself. So as we can see, some basic image processing operations are applied on this image of cat, but we still can recognize the cat. The same was applied in our case. So some rotation, flipping, blurring, or some linear contrasts were used for RGB channels, and some dropouts and hue manipulation was used for digital elevation map. The motivation to use different augmentation for different channels worked pretty good for us, and it just took some fine tuning to find the best combination to not make the model too sensitive or the data too complex for the training. The motivation is to still keep the model converging, you know. to this to describe the overall model's workflow, well, it possesses four steps, for like major procedures. The first one is related to data preprocessing. Basically, we need to normalize RGB channels of the image as well as we need to normalize the digital elevation model. And also from the labels, we need to produce two masks. One mask is of wood objects and one mask is of wood pile borders. Then the first unit model is supposed to be trained on object masks and then produce object predictions. The second unit model is supposed to be trained on border masks and then produce predictions of the borders. And some additional post-processing is supposed to join those predictions and in some simple filtering and processing way to produce the final outcome that can combine those informations. The training and testing of the model, basically to mention a few important stuff, we utilize 14 different aerial maps for training. Each of them contained more than 100 different wood piles, so they were pretty big. And by making use of those smaller cutoffs with some 50 pixel overlaps, we were able to produce more than 700,000 images. Not all of them were used for training. Because of the cross-validation technique, we always mix them somehow randomly and use part of them for training and part of them for testing. As I said previously, both models possess the same architecture, so they were unit models with ResNet 18 encoding. For optimization function, I started with ADAM for but for majority of epochs, the ADAM was used. But at the end, like the last 15 or 10% of epochs were optimized by stochastic gradient descent with very, very low learning rate. Motivation for that was basically when the model was not converging anymore, it hit some decent level. I just wanted to squeeze it a little bit if it was possible by this stochasticity. Sometimes it worked, sometimes it didn't, but I didn't mind. For the loss function, I used pretty normal that is used in similar tasks. So binary cross entropy with logistic log loss. For the batch size, I used number of 35 images. This number was adjusted to be as big as possible, as large as possible, because in these image processing cases, you know, the higher batch size is actually improving the convergency, but actually to make it too big, you can basically overflow the memory. So number of 35 was somehow accurate. The decreasing learning rate is totally standard. I decreased the learning rate in almost linear way. It depended always on how the model was converging. And something about the hardware setup, you know, the 16 cores from Databricks, CPU cores were used for data loading because every time this smaller image was created or taken, then the normalization and everything was proceeded there. So it has been done in parallel way. And then those batches were trained on GPU. As a validation metric, the dice coefficient was taken. So quite important step, I think, was the post-processing, because now we have predictions of objects and predictions of borders. So now we have to join them together and somehow take the best out of both. So basically, the first step of post-processing is to do those predictions themselves. So we obtained the metrics of objects and metrics of borders. Then we are supposed to apply some thresholds on them. It is some kind of level of confidence, and it can be derived from how the network is doing on testing data. And because on object detection it was much better, and our motivation is basically to remove or to mitigate the false hits, then the level of confidence on object detection was much higher. It was like 0.5 or 0.55. So this was thresholded by this level, and the binary matrix was a product of that. From this binary matrix, as a third step, we were able to identify some contours, some objects there, and simply those objects that are too small in size, they were omitted as well, because they were considered as false hits. You know, the wood pile has to have some minimal size, so I think it was like 500 pixels or something like that was the threshold to omit those too small objects. Then we did similar stuff with matrix of borders or mask of borders, but with one difference, and it is the level of confidence, which was adjusted significantly lower. The reason for that is simple. The accuracy of those border predictions was a little bit lower, and also we could afford some false hits there. So basically, whenever some significant confidence appeared, and it was like 0.25 or 0.3, it depends. We took it as a border, as a border pixel. So now we have one binary matrix of object and one binary matrix of borders, and basically we subtracted those borders from objects. So those piles that appeared to be too close together and they were joined by this object prediction, they were separated by this subtraction. Then we were able to identify contours again, and those contours were much more precise. So we don't have so much piles joined together, and for each of them we basically draw them, apply some dilatation, you know, to fix those edges and to smooth them a bit, and export those contours into some JSON format. And at the end we used also some polygon simplification, you know, because some of those edges were not so smooth, and it also produced to us too much of points. So this simplification was worth it to do. We lost minimal information after the operation. So to give you some numbers on test data or test samples, we were able to have like 97 to 98 percent of dice coefficient based accuracy on object detection, which was pretty good, I think. For border detection, we only have around 90 to 94, not 92% of dice coefficient. It varied based on, you know, how data were mixed in cross validation, etc. But what is most important for us is when we put those two predictions together, how it will actually predict the final amount. And the final amount was done separately on digital elevation model, and just to compare it with our previous method, you know, the labeling by human expert, we obtained results that were so similar that the deviation between the previous solution was less than 5%. Actually, in most cases, it was around 2 to 3%. So this is definitely the way how to do it, and the good results for us to proceed it even further. Visualists show you some results. Here it is. These images were not used for the training; they were used only for testing. As you can see, in most cases, those piles are identified pretty correctly. On the left side, we can see one false hit on the left image, as well as on the right image. We can see that probably like 2 piles are not ended well. But there is and how to fix this issue, there is several ways, but now we are implementing an interface for human experts, so he can join to this and he can fix those few piles. So definitely it will be not fully automated solution yet, but definitely we saved some time from human expert already. So that's it. That's all from me. Thank you for your attention, and I'm ready for your questions.